welcome back to my channel. My name is Christine. This is episode 2 of the Subnetting series where we are going to be discussing IP addresses, specifically IPv4 addresses. Before starting off with today's topic, let's take some time to go through the practice questions from the last video. If you have gone through those questions, you can just skip this part and move to the part where we discuss today's topic. First exercise is for binary to decimal. I already have the table made at the top. Now let's look at the first question, that is 00001111. Step 1 is already done, that is to make the table. Step 2 is to place the bits. Now we are going to add the values with the bit value of 1, that is 8 plus 4 plus 2 plus 1, which equals to 15. Hence 00001111 equals to 15 in decimal. Question 2 is all zeros. Here you don't need to go through all the steps. Since it's all zeros, we have nothing to add. The answer is simply 0. Question 3 is 11000000. Step 1 is to make the table. Step 2 is where we place the bits in the table and then we add the values with the bit value of 1. And here it is 128 plus 64, which equals to 192 in decimal. Question 4 is 11100000. Step 1 is to make the table. Step 2 is to place the bits and then add the value with the bit value of 1. That is 128 plus 64 plus 32, which equals to 224 in decimal. Question 5 is 10100010. Step 1 is to make the table. Step 2 is to place the bits, then add the values with the bit value of 1, that is 128 plus 32 plus 2, which gives us 162. Now let's move to decimal to binary exercises. Here I have the table made as well. The first question is 248. So 128 is smaller than 248. We're going to place the value of 1 on 128 and move to the next bit, that is 64. 64 plus 128 equals to 192, which is smaller than 248. So we're going to place the value of 1 on 64 and move to the next bit, that is 32. 128 plus 62 plus 64 plus 32 equals to 224, which is smaller than that of 248. So we're going to place the value of 1 on 32 and move to the next bit, that is 16. Here 128 plus 64 plus 32 plus 16 equals to 240, which is smaller than 248. Place the value of 1 on 16 and move to the next bit, that is 8. So 128 plus 64 plus 32 plus 16 plus 8, or you can just do 240 plus 8, that's easier, but anyway we get 248, the number we want. So for the last time, place the bit value of 1 on 8 and the rest remaining are going to be 0. And the decimal equivalent we get is 11111000. Next step is 168. Here 128 is less than 168, so place the value of 1 on 128 and move to the next bit, that is 64. 128 plus 64 equals to 192, which is greater than 168, so we are going to place 0 on 64 and move to the next bit, that is 32. 128 plus 32 equals to 160, which is less than 168, so place the value of 1 on 32 and move to 16. 128 plus 32 plus 16 equals to 176, which is greater than 168. So place the value of 0 on 16 and move to the next bit, that is 8. 128 plus 32 plus 8 equals to 168, which is the value we want. So lastly, place the value of 1 on 8 and the rest are zeros, and the decimal equivalent we get is 10101000. Next up is 10. In the table, 8 is smaller than 10, so place the value of 1 on 8 and move to the next bit, that is 4. 8 plus 4 equals to 12, which is greater than 10, so we're going to place 0 on 4 and move to the next bit, that is 2. 8 plus 2 equals to 10, that is our number. Lastly, place value of 1 on 2 and the rest all are zeros, and our decimal equivalent is 000001010. Next step is 21. In the table, 16 is less than 21, so we're going to place 1 on 16 and move to the next bit, that is 8. 16 plus 8 equals to 24, which is greater than 21. Place 0 on 8 and move to the next one, that is 4. 16 plus 4 equals to 20, which is less than the value we want, so place 1 on 4 and move to the next one, that is 2. 16 plus 4 plus 2 equals to 22, which is greater than 21. Place 0 on 2 and move to the next one, which is 1. 16 plus 4 plus 1 equals to 21, which is the number we want. Place the bit value of 1 on 1 and the rest all are zeros. Hence, the decimal equivalent we get is 000010101. Lastly, we have 240. So 128 is smaller than 240. Place the value of 1 on 128 and move to the next bit, that is 64. 64 plus 128 equals to 192, which is smaller than 240. So place the value of 1 on 64 and move to the next bit, that is 32. 128 plus 64 plus 32 equals to 224, which is smaller than 240. So place the value of 1 on 32 and move to the next bit, that is 16. 128 plus 64 plus 32 plus 16 equals to 240, which is the value we want. So lastly, place the value of 1 on 16 and the rest all are zeros. Therefore, the decimal equivalent we get is 11110000. Now that we are done with this, let's move to today's topic. First off, let's try to understand what is an IP address in the field of networking. By definition, it is a numerical label assigned to each device connected to a computer network that uses Internet Protocol for communication. It has two main purposes. First is identifying the device, and second is providing the location of the device. Let's try to understand this in a simpler way. Take a city for example. The city is just like your network. In this city, every house is like the device on the network. Each of these houses are identified by their unique addresses. Similarly, each device on the network is identified by their IP addresses. Now let's take a look at the IPv4 address representation. First point is IPv4 addresses are in a 32-bit format. Now in my last video I said 8 bits equal to 1 byte. Here when you take 32 bits you will get 4 bytes. And each IP address is represented in the form of these 4 bytes being separated by a dot. Take a look at the example on the screen, which is 192.168.2.1. Each number has been converted to its binary equivalent, each being separated by dots. These are also called octets. Now let's take a look at the IPv4 address classes. Today we are going to focus on the classful addressing. These classes were originally part of the IPv4 addressing scheme where we had specific ranges for different purposes. First is class A, whose range was from 0.0.0.0 all the way to 127.255.255.255. These were /8 IP addresses. We will get to what /8 means in a while. These class A IP addresses were normally assigned to very large organizations. And the 127 range of IP addresses is reserved for loopback, that is the self-testing IP address. Second is class B IP addresses, whose range extends from 128.0.0.0 to 191.255.255.255. These were /16 IP addresses and were typically assigned to medium-scale organizations. Now we have class C IP addresses, which extends from 192.0.0.0 to 223.255.255.255. These were /24 IP addresses and were usually assigned to small-scale organizations. Fourth is class D IP addresses, which range from 224.0.0.0 to 239.255.255.255. Class D addresses would simply specify the first octet in the range of 224 to 239, indicating that it belonged to class D. They were and are still used for multicast addresses like your OSPF multicast address 224.0.0.5 and 224.0.0.6 fall in this range. Class E extends from 240.0.0.0 to 255.255.255.255. These were initially reserved for experimental purposes and were never officially allocated for public or private IP addressing. Now let's discuss what this /8, /16 and /24 mean. /8 indicates the prefix length of the subnet mask, where the first 8 bits are designated for the network portion of the IP address and the remaining bits are designated for the host portion. Prefix length is what determines your network portion. A subnet mask is a 32-bit binary number or a dotted decimal representation of the network and the host portion of the IP addresses. The network portion of all ones and the host portion is of all zeros. It is the continuous block of ones followed by continuous block of zeros. The network portion is the part of the address that identifies the specific network. The host portion is part of the address that identifies the specific device. Let's understand this with an example. Let's take a class A network, which we will say a /8, and let's take the IP address of 10.0.0.1. This is a class A range IP address, so it will be a /8 network. Remember when I said that the slash notation indicates the network portion? In /8, it means that the first 8 bits or the first octet is the network portion, and the remaining 24 bits are for the host portion, which will help us determine how many IP addresses are available to us. Here you can see the red portion highlights the network part of the address, which will stay the same throughout, and the blue part indicating the host portion will keep changing. Example, we will get 10.0.0.1 or 10.1.0.1, etc. By this, we can also say that the network is 10.0.0.0. For /8, the subnet mask is 255.0.0.0, and it looks like this when you represent it in binary. /16. The first 16 bits or the first 2 octets refer to the network portion. The remaining 16 bits equal to the host portion of the network. Let's take an IP address, say 126.16.4.2. This IP address is from class B range, hence it is a part of the /16 network. The subnet mask for /16 is 255.255.0.0, and when we represent it in the form of binary, it looks like this. The first 2 octets will remain the same, while the remaining octets will keep changing. By this, we can also say that the network could be 126.16.0.0. /24 means that the first 3 octets equal to the network portion and the last remaining octet equals to the host portion. Say 192.168.3.5/24 is a class C IP address, hence it is part of the /24 network. The subnet mask for /24 is 255.255.255.0. The first 3 octets remain constant and the last octet will change. Hence the network will be 192.168.2.0. Now let's try to find the number of usable IP addresses in a network. The formula to calculate that is 2 raised to n minus 2, where n equals to the number of host bits. Why did we subtract 2? And that is for the network and broadcast addresses. They cannot be assigned to any devices. A network address is the very first address that is used to represent the whole network, like 10.0.0.0. The broadcast address is the very last address that is used to send broadcast messages to all devices on the network. So for the 10.0.0. network, the broadcast address will be 10.255.255.255. Now back to what we were discussing, let's try to find the usable addresses in 192.168.4.3/24 network. /24 means that the subnet mask is 255.255.255.0, which when written in binary looks like this. Now notice how the last octet is all zeros. It is our host portion. There are 8 bits in the host portion. N equals to 8 here. So 2 raised to 8 minus 2 equals to 254 usable IP addresses, which can be assigned to devices. Now let's take a look at the range. As I said, for /24, the first 3 octets remain the same. The last octet will change. So the range will be from 192.168.4.0 to 192.168.4.255. This is including the network and the broadcast address. Now let's find the first usable IP address. The first usable IP address equals to 1 plus the network address. Here it is 192.168.4.0 plus 1, which equals to 192.168.4.1. Let's find the last usable IP address, which equals to broadcast address minus 1, which is 192.168.4.255 minus 1, which gives us 192.168.4.254. Now let's try for /16. Say 172.16.0.0/16. When we say /16, the subnet mask is 255.255.0.0, which in binary looks like this. The last 16 bits equal to the host portion. Here n equals to 16. Putting it in formula, we get 2 raised to 16 minus 2, and where we get 65,534 usable IP addresses. The range for /16, the first 2 octets remain the same, and the last 2 octets will keep changing. So it will be 172.16.0.0 to 172.16.255.255. The first usable IP address equals to 172.16.0.0 plus 1, which will give us 172.16.0.1. The last usable IP address equals to 172.16.255.255 minus 1, which gives us 172.16.255.254. Let's take a look at slash 8. Say 10.0.0.0/8. When we have slash 8, the subnet mask is 255.0.0.0. We have 24 host bits here, so n equals to 24. 2 raised to 24 equals to 16,777,214 IP addresses. The range is from 10.0.0.0 to 10.255.255.255. The first usable IP address is 10.0.0.0 plus 1, which will give us 10.0.0.1. And the last usable IP address equals to 10.255.255.255 minus 1, which gives us 10.255.255.254. Now one more thing that we can do here is suppose say I need the fifth usable IP address. I can do this too from the range that we get. Say for 192.168.4.0/24, the first usable IP address would be 192.168.4.1. Then comes 192.168.4.2. The third IP address would be 192.168.4.3. The fourth would be 192.168.4.4. And the fifth would be 192.168.4.5. That there it is, our fifth usable IP address. Now all of this that we discussed is in the format that was followed way back in the nascent stages of the internet. Here the problem you notice is that there is a huge wastage of IP addresses. Take a look at slash 8 range. We have 16,777,216 IP addresses available to use. Even if I was to give this to a very big organization, they won't be able to use all of it, leading to wastage of IP addresses. This also led to the exhaustion of IP address spaces. The second is your routing table growth. If I was to advertise the slash 8 network, just imagine the size of the routing table. Due to this, the lookups would slow down and it would increase the size of the routing table, leading to excessive resource utilization. Looking at all of this, the solution that was implemented was CIDR, which is classless interdomain routing. This removed the requirement of having fixed block sizes. The network can now be segmented on the basis of prefix length and not classes, and the networks can be divided into different block sizes, that is the VLSM, variable length subnet mask. This is what we are going to discuss in the next episode. Before ending this video, there are some exercises for you to try. If you do try them, let me know in the comment section down below, and if you get stuck on them, we'll discuss this in the next episode. So that's it for today. I hope you enjoyed it. Don't forget to like and share this video with someone who might find it useful, and subscribe for more updates like this, and I'll see you next time. Bye.